Hi everyone, today we're going to talk about section 10.3, chords. So we have a warm-up here that says which figures in the diagram are congruent. How do you know? Find all remaining segment lengths in the two triangles. So if we're looking at these two triangles, a couple things that you want to notice is that 123 degrees is the same in both circles. So I'm going to go ahead and mark these two angles congruent. Okay. Now, if this side of my triangle is 3, we call that a radius because it's a segment that goes from the center to the circle. Now, that would mean that the other radius is also going to be 3. And we can do something similar on the second circle. So one radius is 3, the other radius is also 3. Now, obviously, all these segments are congruent to each other because they all have a length of 3. So are the two triangles congruent? Well, they have to be. So triangle BAC is congruent to triangle EDF by side angle side. So we're bringing back the same triangle congruence as we saw earlier in the year. Okay. Now the circles themselves are also congruent. I can say that circle A is congruent to circle D because they have the same radii. Okay, remember radii is just plural for radius. So if we want to mark the remaining sides, well, I have all of these. I know that by CPCTC, that long side has to be 5.27. Okay, now what we just dealt with in this diagram is a segment, that long segment that we have connecting these 2 points, as well as this one. Those are both called chords. So a chord is a segment whose endpoints are on a circle. So if we look at this diagram right below, give it a couple letters. Let's call this A, let's call this B. We would label it AB is a chord. Okay, we use the same notation as any segment with that bar right above it. Now I'm going to have you guys take a couple minutes and see if you can use congruent triangles or anything we've talked about with triangles and circles to answer the following questions. Go ahead and hit pause and try these problems. If we're looking at example 1, we know that the 4 radii all have to be congruent because they're in the same circle. And we also know that the vertical angles are congruent. So if you look at these two triangles, the triangles have to be congruent by side angle side. Now as a result of that, RS is congruent to TU, again by CPCTC. So we could have made this into a 2-column proof. I'm just doing it a little bit shorter, just summarizing the main key points instead of setting up the 2 big columns. Likewise, in our second problem, why are the angles congruent? Well, again, we've got these 4 radii congruent. And so the triangles are congruent by side, side, side. And therefore, angle CAB, right here, is congruent to angle DAE by CPCTC. Okay. All right, so let's jump to our next page. And those couple example problems lead us to some theorems about chords. So within a circle, or congruent circles, congruent central angles have congruent chords. So I'm going to show you guys in this first diagram, if these two central angles, actually let's look at the wording on here. If MN, so if we have congruent chords, then our central angles are going to be congruent as well. And it works both ways. So the converse is also true. Yeah, let's write that here. Converse, also true. So if I have congruent central angles, then the chords that they create are also going to be congruent. Likewise, if you have two congruent chords, then the central angles are going to be congruent. Now our second theorem says congruent chords have congruent arcs. So if I were to look at, actually let's look at this one. So we're talking about the arcs, MN, I'll use a highlighter, it's a little easier to see. So MN is congruent to PQ. Okay, it's kind of hard to tell. That should be a Q. Didn't print very well. So if you have two congruent arcs, then the chords created by the endpoints are also going to be congruent. Okay, so for the second one, really what we have here is the converse. So the converse is also true. So it works in both directions. Okay, so if the chords are congruent, then the arcs are congruent. If the arcs are congruent, then the chords are congruent. And finally, the last one says congruent arcs have congruent central angles. Okay, so actually let's draw a third picture. I didn't include a diagram for this one. Pretty much combines the other two. So if we were to draw a circle, okay, if I have congruent arcs, so let's do that here. And I don't even need to put them across from each other. Let's just do it like this. So if I have a diagram that looks like this, and let's say these two arcs are congruent. I can even put a little dash marking on them. Okay, so if those arcs are congruent, then the central angles are congruent as well. So they're all three of those are related to each other. So we've got the chords, the arcs, and the central angles. Okay, and actually I guess we can write here as well. Converse, also true. Okay. So if we jump down to example 1, it says the two circles are congruent, so we need that. Given that BC, so arc BC, is congruent to arc DF, what can we conclude? Well, we can conclude a couple things. We know that our central angles are congruent, so we can say angle BOC is congruent to angle DPF. And we also know the chords are congruent. Okay. So the next part says, well, what if we were given the chords are congruent? Well, all the rest is going to follow as well. Then the central angles are congruent, and the arcs are congruent. I could label them the way that we did up top, but we already have them all listed there. So, all right, now our next couple theorems say within a circle or congruent circles, chords equidistant, we see that word a lot, equidistant, from the center are congruent. So if we have these two segments congruent to each other as it's marked on the diagram, okay, that means that the distance from chord DC is the perpendicular, right? Distance is always perpendicular. So the distance between this chord and the center is going to be this segment FS. Likewise, up here, ES is the distance to chord AB. So if these two segments are congruent, then the chords AB and CD would have to be congruent as well. Okay, so this chord would have to be the same length as this one. Okay, the converse is also true, which is right here. So congruent chords are equidistant from the center. So if the chords are congruent, then FS is congruent to ES. Okay, so if we know that the lengths of, use the highlighter again, the lengths of these two segments are the same, that must mean that those two segments are congruent as well. Okay. All right, let's flip to the next page. And we'll do the first problem together. So you'll notice in this diagram that I have a chord up here, down here actually, and a chord up top. Now, the distance from the center to the chord is 9, and the distance from the center to this chord is also 9. So since they're equidistant, the chords have to be congruent. Now you'll notice that these two parts of the segment are marked the same. So I know that we have to have 12.5 here as well. So the total length of PR, adding these together, is 25. Well then, my other chord, labeled with A, would also have to be 25. All right, looking at the next problem, I want you to take a look real quickly and see if you can find the value of X. Go ahead and press pause. All right, taking a look at our second example, one of our chords is 36 units long. The other chord is 36 units long. That means they both have to be equidistant to the center. So X would have to be 16. Not too much more going on there. All right, so our last few theorems say in a circle, a diameter that is perpendicular to a chord bisects the chord. And to understand this, I'm actually going to look at this picture. You'll notice that I have chord AB drawn in, and there's a diameter that cuts through that chord. So a diameter is just 2 radii, goes all the way through the center. Now, one of the things that happens is that these two sides are congruent to us, okay? And since the diameter is perpendicular, I'm gonna go ahead and mark this as a right angle as well. And you'll notice that we also have this reflexive side right in the middle. So these two triangles are actually congruent to each other. We're not doing a proof here, we're just making an observation. So because the triangles are congruent, BE has to be congruent to AE. So really what we did was we just proved that if the diameter is perpendicular, then it bisects the chord, okay? And the other thing that comes along with this is that if a diameter bisects a chord, then it has to be perpendicular to the chord. So it's just the converse of what we just talked about, okay? And then finally, the perpendicular bisector of a chord has to contain the center of the circle, okay? Because we know that if it's the perpendicular bisector, it has to be the diameter, okay? So if you guys look at this picture over here, if you have a perpendicular bisector, okay, that means it goes through point S, which is the center of the circle, okay? So a lot of times with these diameter and perpendicular type problems, really what we're dealing with are right triangles, That's really the main thing. And it's because of that perpendicular portion. It makes a right angle. So let's say, for example, I have a perpendicular from the center hitting a chord. Well, that means the chord got bisected. You can always split it exactly in half. So each of these pieces would have to be 7. Now, if I'm looking for the radius, you'll notice this is now a right triangle. So how do we find a missing side in a right triangle? We use Pythagorean theorem. So what is that, 58? Round to the nearest tenth. I'm just going to take the square root in my calculator. So we have the square root of 58, 7.6. Okay. When we look at the second example, notice that the segment that starts at the center hits the chord. It bisects the chord, even though it kind of doesn't look like it. It's not the best picture. But because these two are both 11, I know I have a right triangle. So if it helps, draw the right triangle off to the side. Let's say this is 11. That's Y. This is 15. Notice it's across from the right angle. And we can use Pythagorean theorem. Do some subtraction. Take a square root. And we have 10.2. Okay, so with those right triangles, a lot of times you will see Pythagorean theorem. All right, let's go ahead and flip to our last page. You'll notice there are 2 problems on this last page. This is the end of the video. You guys can walk through both of these and give them a try. I will be posting the scanned notes, which will include these fully worked out, so you guys can check your answers when you're finished. That's all for today. Homework is due Tuesday night at 11:59. Make sure you guys are showing all of your work. Again, if you don't have a printer, you can always write out the problems on a separate sheet of paper. And that's no problem as long as you show your work. That's all for today. Have a good day.